Now, let's look at continuous mixture distributions. Here we consider a continuous mixture of discrete distribution where the relationship is flipped. Suppose that the single day number of COVID positive cases in a university in the US, given some rate lambda, follows a Poisson distribution with rate lambda, where the PDF is given by the fx over here. And we note that the x, which is the count of the daily positive cases in the university, is going to take possible values between 0, 1, 2, all the way up to infinity. And different university can vary in size, location, the scale of their testing programs, and also their level of restrictions. So the rate lambda, note that here we have used the capital lambda, is also random. So we use capital lambda to indicate that the rate of the Poisson distribution itself can be a random variable. Let's assume that large lambda, capital lambda, is distributed as a gamma AB random variable in the whole population of all US universities. And here we know that the gamma AB random variable has the following PDF. I'm not going to read it here, I'm just putting it here as a reference. So if we want to draw samples of single-day positive cases in US universities, let's call it X, this is quite similar to the discrete case. So step 1, for each I between 1 and n, we want to first draw the rate, so the lambda. We want to draw the lambda I, which follows the gamma distribution with parameters a and b. And this is going to be the Poisson rate for that particular sampled university. So we know that for a Poisson random variable, which is very useful for modeling counts, its expectation, the Poisson random variable with rate lambda has expectation or mean equal to lambda. So we know that the higher the rate, the larger the expected number of positive cases for that university in a given day. So step 1, we have drawn the Poisson lambda parameters, which is the rates for the randomly sampled universities. In step 2, for each of the i's, we want to draw the actual number of counts for the COVID cases, which is a non-negative integer, which will follow the Poisson distribution of rate equal to the lambda I that was drawn in the first step. Let's try to implement this in R. We'll call this thing the Poisson gamma mixtures. So this is actually the name that this mixture distribution is known for. So let's draw 1,000 samples, which we denote by xi's, I from 1 to 1,000, from the Poisson gamma mixture distribution, where x is distributed, x given lambda has Poisson distribution with rate lambda, and lambda is distributed according to the gamma distribution with a equals 100 and b equals 5. So let's implement the 2 steps in the code chunk below. The first line of code implements step 1, drawing the lambdas from the gamma distribution. So here we create a vector of length 1000 called lambdas, and they are going to be random draws from the gamma distribution with shape parameter equal to 100 and rate parameter equal to 5. So a of 100 and b of 5. We use the built-in R gamma function to do this. In step 2, once we have the lambdas, which is the Poisson rates for each of the sampled universities, we're going to draw the actual number of positive cases for each of the schools on that day. So we're going to use the built-in R sampler for the Poisson distribution, R+, and we indicate that we want to draw 1,000 samples. And for each of these samples, the rate parameter is in the lambdas vector we drew in step 1. And the impulse vector, which is also length 1000, will be the draw of the number of positive case counts of the 1000 random universities in the US. So there is a math stats result that you might or might not know. So here's the result. So under this Poisson gamma mixture distribution, the xi's, so the marginal distribution at the end of our counts of positive cases, will follow the negative binomial distribution with the number of successes we want equal to a, and the success probability equal to 1 over 1 plus b. So note that A and B here actually correspond to the parameters of the gamma distribution. So for our example, we can see that the x's we sample will end up following a negative binomial marginal distribution with the size equal to A, so 100, and the probability of 1 over 1 plus 5, which is 1 over 6. So why is that? I'm just going to briefly talk about the idea of the proof. So to show that the marginal distribution of xi's from the Poisson gamma mixture follow the negative binomial distribution, we can try to work out the marginal density of x. So by definition, the marginal density of x, f large X of x, is equal to the integral from 0 to infinity. So these are the possible values, all the possible values of lambda, the Poisson rate, of p of f of x given lambda times the density of f of lambda under the gamma distribution d lambda. Essentially, what we're doing over here is just applying the continuous law of total probability, where we try to get the marginal distribution by integrating out the other thing. So in this case, the other random variable is lambda over its support. And over here, we can plug in the corresponding distributions. We know that fx given lambda is the Poisson distribution with rate lambda. So this is the PDF for that. And we also plug in the gamma density for the lambda. So the Poisson rate, and it's this part. The actual calculations and derivations will be omitted here because it is a little bit involving and it's not super relevant to what we want to do over here. So let's just assume that the let's take a leap of faith that the math works out. And at the end, the fx of x comes down to the negative binomial density with parameters a and 1 divided by 1 plus b. So in that case, the density is given by this negative binomial PMF over here, where the probability that x takes the discrete value of small x is equal to x plus a minus 1 factorial divided by x factorial times a minus 1 factorial times 1 minus 1 divided by 1 plus b. You can see that's our probability to the 8th power and 1 divided by 1 plus b, or p to the x power. So that's the definition of the negative binomial density. So here, let's just numerically compare the density of our mixture draws, MPOS, number of positive cases, the 1000 draws, with the theoretical negative binomial a equals 100 and p equals 16 PMF. So again, we compare the empirical and the theoretical densities. The empirical density is like before, we just graph the histogram with frequency equals f. For the theoretical density, there is something to note over here. So first of all, we can see that in this case, the negative binomial distribution is a discrete random variable, meaning that its support is actually it's actually a discrete distribution. So the possible values of x are integers, so 5, 6, all the way up to 35. I'm just plotting this range over here. And then we can use the built-in R function, dn binom. N binom stands for negative binomial, to try to find out what is the corresponding probability mass for each of these possible outcomes between 5 and 35. If you read the documentation of this function, or in general the functions for documentations for n binom in R, you will find out that R's parameterization of the negative binomial distribution is slightly different from ours. So in this case, we have to slightly alter the inputs when we use the d n binom function. The first is that we are going to, instead of use x plus 1. And the second thing is that when we input the probability, instead of using the p over here, which is 1 over 6, we input 1 minus p, which is 5, 6. And so this fx is the corresponding probability mass for each of these possible outcomes, x-axis. We overlay this on the empirical density of our impulse draws, and we can find that they agree quite well, meaning that it does seem like the mixture draws we obtain in this way indeed follow the corresponding negative binomial distribution.